Good afternoon, everyone. Welcome to the tutorial led by QuEra and the Pawsey Supercomputing Centre on neutral quantum computing. My name is Tommaso Macri. I'm the Executive Account Manager at QuEra Computing. And today I'm happy to introduce my esteemed guests from both QuEra as well as from the Pawsey. The first one is Ashutosh Kumar, who is a senior quantum application scientist at QuEra, working within the algorithm and applications team. Then we will hear also from my colleague Anshuman Singh, who is a senior photonics engineer. He will be presenting about the activities in photonics at the company. And our collaborator from the Pawsey Supercomputing Centre, Pascal Elai, who is the quantum supercomputing research lead. So thank you, Ashutosh, Anshuman, and Pascal for joining this webinar. The agenda for today will be structured in a series of presentations that will cover aspects of the activities from QuEra, starting with the general introduction about our company and our technology. Then Pascal will take over and discuss some recent applications stemming out of the collaboration between Pawsey and QuEra on analog quantum computing with neutral atoms. Then we will pass the word to my colleague Anshuman, who will discuss some recent developments in photonics within the company. And finally, Ashutosh will cover the application areas of digital quantum computing with the platforms that we've been developing at QuEra. I would also like to remind that to the first 20 registrants within for this specific webinar, we will also be offering, with the kind collaboration of our colleagues from Pawsey, 1 hour of access to our quantum computer Aquila, which is a 256-qubit machine. I will describe its capabilities in a couple of slides. And you will be receiving an email with the details regarding this opportunity. So why don't we start? Let me first tell you a few words about the company. QuEra is a quantum computing company based in Boston, next to Harvard and MIT, who turn out also to be our very close collaborators. The mission of the company is to build quantum computers based on a specific technology that is called neutral atoms. Neutral atoms turned out to be also extremely promising to realize scalable and fault-tolerant quantum computing, as we will see throughout the presentation. As part of our commercial engagements, we also offered the access to our first generation quantum computer on a major public cloud starting in November 2022. And now this will be, and the applications on the specific hardware will be actually the topic of the presentation by our collaborator Pascal. QuEra now is focused on a number of applications that we believe are definitely relevant for current and upcoming generations of quantum computers, such as simulation, machine learning, and optimization. Let me tell you why neutral atoms are actually extremely relevant for the development of the field of quantum computing. So first of all, neutral atoms are kind of nature's perfect qubit. They are all identical, and therefore they respond to external fields all in the same way, meaning that they don't need individual calibration in order to assess their properties, to calibrate, and also to characterize their properties when we want to perform any type of analog or digital computation. Secondly, right now we have systems with hundreds of qubits. We have demonstrations actually with more than with few thousands of qubits at the Harvard lab. The latest demonstration reached 3,000 qubits, and this was a result from a couple of weeks ago. And we believe that our systems can scale up to several tens of thousands of qubits without requiring complex interconnects. Moreover, there are certain capabilities that make these systems particularly efficient in terms of reconfigurability of their layout, not only from shot to shot, but also during the computation, in such a way that we can encode the problems efficiently and perform quantum error correcting codes or algorithms without many limitations related to the to kind of fixed topology or fixed connectivity. Last but not least, the systems that we are developing operate at room temperature, and therefore reducing the complexity of having cryogenic devices attached to our computers, but also at the same time decreasing the footprint of the machines that turn out to be extremely important for organizations such as, for example, Pawsey, that might be interested in integrating our systems with the current generation of high-performance supercomputing systems. The first generation of our quantum computers is called Aquila. It's a 256-qubit machine, still the world's largest quantum computer available on a public cloud in terms of number of qubits. Over the past 2.5 years, we increased the availability window from hours per week to more than 100 hours, allowing researchers and customers all over the world, including India, to access essentially the system almost in real time. As I mentioned, we are focusing on a few strategic areas of applications, such as simulation, optimization, and machine learning. And all these activities have led to a number of important scientific collaborations and related high-impact publications. The way to access this model or this machine is either through the service from AWS called Bracket, which is the service from Amazon that offers quantum computing services through the cloud, or through dedicated direct access by reaching out to us at QuEra. More in detail, there are among these 3 different pillars for related to the applications of our quantum computing systems. I want to mention machine learning, and more specifically, machine learning that is enabled by quantum systems, for example, for the purpose of classification or regression and prediction. And in particular, within this area of application, we also developed one specific tool that we call the quantum reservoir computing that is particularly suited to the current capabilities of our first generation quantum computer. The second area is the one of that we call combinatorial optimization, that is based on the solution or minimization of a complex cost function that in principle has a multiple number of optimal or suboptimal solutions to choose from. One class of problems that are particularly suited to be essentially solved with this device are what are called the maximum independent set problems, which turn out to be a kind of native problem that can be addressed by our devices. There are also other non-native optimization problems that can be mapped into problems that can be solved by Aquila, for example, quadratic and constrained binary optimization problems that turn out to be relevant for commercial applications. The third area, which is the one that we would define quantum simulation, that was initiated more than 40 years ago by the Nobel Prize winning physicist Richard Feynman. Essentially, it aims at tackling problems that are inspired by either fundamental physics or chemistry applications, such as the equilibrium or non-equilibrium phase of matter, as well as the study, for example, of lattice gauge theories. If you're interested in learning more about this specific set of applications, I would definitely point you to the so-called Aquila white paper that we put on the archive already a couple of years ago, and details a little bit more the broad spectrum of applications with our machine. The second generation of quantum computers is what we call the Gemini-like series. Is now on a digital quantum computing paradigm. It has still a few hundreds of qubits, and the first unit has now been installed at AIST, which is one of the leading supercomputing and research centers in Japan, alongside the so-called ABCIQ supercomputing system that will host a few hundreds of NVIDIA's GPUs. So realizing with the goal of essentially potentially connecting or integrating both quantum and classical nodes within the same setup. A picture of the machine in this current form is represented here in the picture on the right, and as you see, it is made of a number of racks that represent the classical control to the quantum processing unit or QPU, which is sitting in the middle of the device. In terms of positive sides related to the possibility of integrating such devices to within HPC centers, I want to mention the important feature of the relatively low power consumption compared not only to other devices or to other technologies, but also, and probably most importantly, with respect to the existing typical consumption of high-performance supercomputing centers. So this is also a kind of message for those of you that might be working with supercomputing systems in India. If you're interested in looking at a specific opportunity to integrate a quantum computer with your current systems, this could be potentially one of the kind of preferred solutions to look at. Another important area in which QuEra is definitely making really a lot of progress is quantum error correction, for which we were named essentially, or our contribution together with, of course, our academic collaborators from Harvard, MIT, and other top institutions nationally and internationally, as the breakthrough of the year from Physics World in 2024. And as you can see, this achievement builds actually on top of a number of important publications that are both based on experimental as well as on theory work. Our recent results on the experimental demonstrations of logical magic state distillation have also been recently published in the journal Nature a week ago. So what is the best way to potentially work together with QuEra? QuEra, in a way, for many quantum computing applications, essentially would become your quantum innovation partner of choice. We basically work across three main different verticals. One which is related to the possibility of having access to cloud or on-premise machines that come along with the installation, support, and community development. The second pillar is focused on collaborative research, for example, on areas that are strategic for the development of this field, for example, quantum error correction or the development of hybrid quantum classical algorithms. And the third one is focused more on applications, both for academic purposes as well as for more industry-related areas, which is an area that we call application co-design. And the focus or the goal of application co-design is to really make sure that we can match the current capabilities of our existing or upcoming quantum computers with some very close or tight development of at the application level to make sure that we get the most out of a specific application or algorithm to be designed in collaboration with our scientists at the company. As part of our engagements with the current quantum ecosystem, last year we launched the so-called QuEra Quantum Alliance that by now counts with more than 20 partners from all over the world, and spans not only across the space of pure play quantum computing companies at the software level, but also with very relevant partners, for example, the Pawsey Supercomputing Centre that works specifically within the area of classical supercomputing systems, and they share their expertise in order to increase the possibility of having an impactful or designing impactful applications that can benefit from classical and quantum devices. The goal of the present or the activity that we are presenting today, this webinar for the Indian community, is actually the result of a number of activities that we've been developing together with many collaborators in India. That started back in July 2024 with a week-long business mission to India, visiting a number of academic and industry partners, followed by a webinar dedicated to our Indian colleagues that dates back to December 2024, as part of a series of webinars that we call QuEra with Friends. Then, as part of the upcoming activities, my colleague Ashutosh Kumar will be attending Quantum India that will take place in Bangalore at the end of this month. So I would like to take this opportunity to emphasize the possibility of really relating or connecting directly with our team in presence if you are going to attend this event in about a week from now. Of course, if you're interested in exploring any type of collaboration, feel free to reach out to us. I will reinforce this message at the end of the presentation. So, last but not least, before leaving the word to my colleague from Pawsey, I would like to highlight that for those of you that will stay until the very end of this webinar, we will be also selecting one lucky participant to receive one of our very cool Lego set that represent our second generation quantum computers. So with this, I would like to thank you for attending the webinar so far, and of course, I hope that you can stay until the very end. We will now start diving deeper into the technical side of this webinar with the contribution from my colleague Pascal Eli from the Pawsey Supercomputing Centre. Pascal, are you able to share your presentation?
Yep, let me share. Okay, let's see if it's gonna, let me just share this one. And then, so there we are.
In the meantime, while you share, Pascal, let me remind that we also have a Q&A that is going live as we speak. So if you have any questions, any curiosities, feel free to ask questions. I will be available to answer, as well as my colleagues Pascal, Anshuman, and Ashutosh. Pascal, the floor is yours.
Thank you. Thanks, Tommaso. And I should point out that I was one of the lucky people that have the Lego set. So it's actually on my desk, and I had a lot of fun building it with my kids. So it's a very cool Lego set. So as Tommaso kind of mentioned before, supercomputing, quantum computing are now sort of at a turning point of actually trying to integrate these two different types of technologies. Pawsey is a supercomputing center, but we are actually really interested in trying to look at quantum computing technologies. And I figure it's a good idea to give a bit of context, and then I'll do a deeper dive into neutral atoms and some of the research that we're doing. So this presentation is giving you a sense of why we are exploring quantum computing and what we're trying to do. So yes, it's accelerating quantum computing and supercomputing, and talking about the Quantum Supercomputing Innovation Hub, which I lead. There we are. So I'm actually based in Australia, and actually one of the traditions that we have in Australia is an acknowledgement of country. So Pawsey actually sits in Perth, but it also sits on the traditional lands of the Noongar Whadjuk people. And so I'd like to pay my respects to their elders and past, present, future, and their ancestors as well. And actually, we have a strong connection to the First Nations people of the area. This in the slide is a painting of meteorites as seen by a Wadri Yamaji person up in the northern area of Western Australia. And it actually sits on the supercomputer that sits in the background. So this is the Photonics supercomputer of the Pawsey Supercomputing Centre. We've got the artwork there. I'm not actually obviously in the white space. I just have a nice background. But this is principally the primary focus of Pawsey is this type of supercomputing. So Pawsey is actually Australia's national high performance computing center. It's the largest supercomputing center for research. So we are research oriented and we strive to be at the cutting edge of technology, and our domain is scientific computing, right? So we are a research organization, but we also try to help universities and researchers do novel science and providing world-class supercomputing infrastructure and expertise. But the big thing is we also try to be at the cutting edge of technology. And that's where quantum computing comes in. So to give you a sense of what we do, right? Pawsey is involved in a wide variety of actual scientific research, from astrophysics to molecular dynamics, to DNAs, to looking at AI, to looking at machine learning techniques. We've got about 200 research projects that are active, 4,000 users, lots of different scientific fields. All these scientific fields currently are really heavily focused towards just classical scientific computing. But of course, there are some interesting challenges there to solve that could benefit from quantum computing. We also are a national leader, so we have done research such that we have helped teams win the Gordon Bell Prize for computing. So that's the equivalent of like a Nobel Prize for large-scale computing, looking at the Giuseppe Barcel, looking at quantum chemistry. So not quantum computing chemistry, but chemistry, like quantum simulations of chemical models. We've also actually been involved in a collaborative effort with a local quantum computing company that actually led to one of their founders winning a Prime Minister Award. So we really try to be collaborative in our approach. This is something to note. And that's the entire purpose of the Quantum Hub, right? This supercomputing quantum mediation hub is meant to be a collaborative platform focused on integrating quantum computing with classical scientific computing. And it's really meant to accelerate the application of quantum computing to real world problems, not just like looking at quantum computing research on its own and in isolation to assist that research, but also then to try to connect that research to scientific domains to solve a problem. Rather than, let's say, solving the problem of quantum computing, it's the idea of making quantum computing solve a problem. So the hub itself has got innovation, education, and inspiration as the three pillars. We are involved in educating and trying to come up with educational programs for young kids, primary and high school, really inspiring them to take up look in quantum computing, scientific computing. At the university level, we are involved with the University of Western Australia heavily with educational programs, but also like actual research. And then the innovation happens because we are working with tons of researchers in quantum computing, working with QuEra, right? Working with a wide variety of people trying to tackle some really interesting, complex challenges. Some of those innovations have to do with actually trying novel classical technologies, but dedicated to quantum computing simulations. We have an entire cluster dedicated to simulating quantum computing so that people could then try on real hardware. We were actually the world's first center to deploy a quantum computer in a supercomputing environment. So in a data center, it's a small sort of diamond-based technology quantum computer. This is an Australian startup called Quantum Brilliance. But we're also very keen on democratizing quantum access. Tommaso mentioned AWS Bracket, that you can access QuEra devices or cloud computing devices. We are very keen on trying to provide a model which Australian researchers and their collaborators can get access to real-world quantum computing devices with like a merit allocation scheme. So part of the way we operate in Pawsey is that people propose scientific challenges that they want to use computing resources for. They say, this is the amount of computing resources we need. This is why we need them. And this is the question we're trying to answer. And normally we're aiming for something similar for quantum computing, where people would say, this is my quantum computer. This is the scientific question I want to answer. And this is why I need classical and quantum computing resources to tackle this scientific question. I should just briefly show this idea of the inspiration education. We had boot camps for researchers, right? Because a lot of researchers don't actually have quantum computing literacy. So we actually ran boot camps dedicated to actually like domain specialists that are non-quantum computing. And the stop motion video is like a quantum day event we ran for World Quantum Day, educating kids and parents and basically the public about quantum computing. Right. So the hub is actually a small team. Myself, Shusen, Edric, Uwe Vredo is the acting director. Casey Myers is a Pawsey in UWA. So he's a researcher, a lecturer at the University of Western Australia, and also a member of the Pawsey Supercomputing and Quantum Computing team. We focus on integration of HPC with quantum computing, high performance quantum computing simulation, and quantum algorithm development for both near and far term hardware, right? So that's kind of the main focus of what we do. Just to note that one of the things that it's obviously challenging for quantum computing simulation, because it's important to kind of do some of these simulations before moving to hardware, is that we actually do a lot of large scale quantum computing. I don't know if people in the audience have played with stuff like Penny Lane and Qiskit and Blockade. Normally the simulations, or even Bracket, normally the simulations you can do, most people play with simulations that can run on their laptop. But once you get to really trying to get a large scale simulations, you need supercomputing centers. And so we are there to also assist that. We also do trying to do high performance simulation of quantum circuits because the resource footprint is very large. I'm going to skip the computing on this aspect, but just the fact that we have really gone through and dedicated quite like real significant resources to do the algorithm design, so that people can do simulations of quite large scale algorithms like quantum circuits, so that they can then migrate to real world technology without a huge challenge. So we've got an entire cluster dedicated to that. We've developed actually our own libraries, looking at quantum computing acceleration with GPUs. And so there's a real sort of side that is not necessarily quantum algorithm focused, but because we can collaborate with people, this ends up assisting quantum algorithm research. So the other bit as well is this quantum computing integration. So as Tommaso mentioned, ACE has a deployment of a new QuEra device. But there's an interesting challenge for supercomputing centers for deploying quantum computers, because the standard practice for big data centers is that you can always just replace components. So Photonics, for example, will burn through its GPU every couple of days and get a GPU replaced, right? And that is the nominal known process, and that's and we also know how to operate all of this. The intersection is a bit more complicated, right? We want to get to the point where we can run the portion of a real world problem that can use quantum acceleration, the portion of a problem that requires classical computing without having to worry all the details. And so that's some of the work we've been doing, developing the qubit bridge, which is looking at hybrid workflows. So not just running stuff, let's say on QuEra, on Blockade, like using Blockade to chat to the Aquila computing's quantum computer, but also using Aquila to run on the quantum computer while other computing happens to make use of, let's say, an optimization answer in a larger system. And so that has been part of our work. We're actually looking at also forward focusing where we have many QPUs. So we are running integration setups where we run virtual QPUs, not with one quantum computer, but with many. The idea of having possibly either on-premises access or cloud access. We've got a setup, we've developed a technology that allows either. I'm happy to go through the videos, but I feel like probably we'll do more keep this in Q&A if there are further questions. But it's actually been recognized as like a nominal real innovation. So we recently won an award for this qubit bridge that integrates supercomputers and quantum computers. And we're looking to apply this to real world problems from machine learning techniques, like computer vision classification and so on, where classical methods might be initially better, but there might be some really interesting application for classification and maybe not detection that could really benefit from making use of like quantum kernel techniques. So then normally the pipeline of processing an entire swath of data, training it, and then having the pipeline be able to take new data and produce detections, classifications, and everything else requires classical and quantum. So this is why we're working on this. We're all looking at democratizing access. So as I mentioned before, we are looking at trying to allow access to quantum computers. There are not many in the world. We've been fortunate at Pawsey to actually have a real collaboration with QuEra to kind of enable this, but we'd like to branch it out to more than just, let's say, Pawsey research staff, but to everybody, and provide a nice control for budgets and costs to allow researchers to access classical hardware and computing hardware and then run those hybrid workflows without having to worry about accounting, budgets, all the normal other bits of infrastructure that you would have to develop and deploy to kind of make this stuff happen. So collaborations, we are growing many collaborations. We've got, as I mentioned, of QuEra, and we work with AWS, and QuEra has also worked with like AWS and NVIDIA. So we work with a wide variety of quantum computing vendors or industry players, as well as research institutes, and also even national labs like Oakridge National Labs. And we're hoping to build that collaboration with also India and so on. So now to kind of focus on the QuEra partnership. So I wanted to mention the QuEra Quantum Alliance because it's been a very productive alliance of looking at a variety of projects. So I'm not going to go into all the projects, but I would say that it's been really a collaborative approach to looking at applying quantum computing algorithms or designing quantum computing algorithms to tackle a variety of problems. And it's not just Pawsey, like we have obviously researchers from the University of Western Australia. So Western Australia, the University of Western Australia is located in Perth. We have a strong partnership with them. The national level research organizations, but also even the international. So we've got people who are based in the States that we're looking at trying to combine our knowledge of making use of neutral atom technologies, and ACE in Japan, because they also have a new QuEra device, but we're looking at the intersection again. They're a supercomputing center more interested in looking at solving scientific or industry challenges, not necessarily the details of quantum computing, but they want to enable quantum computing to solve these challenges. So let's go through here. We'll just mention some more details about projects, and I'm happy to take questions down the line about the specifics of these. But these projects have been focused on looking at using the analog QPU, Aquila, looking at optimization, where we're looking at using different algorithms to explore optimization, quantum machine learning. We actually have a student that's kind of leading this, looking at quantum reservoir computing and predicting health outcomes, looking at health data, but also looking at detection, classification of radar imaging data, and also have a project that is on the modeling of quantum systems. So we've tried to sample kind of almost everything. The only thing that is not sampled here is chemistry. But the quantum system always kind of falls into that, but we're actually looking at more quantum phase transitions, looking at some more esoteric phenomena. But the idea is to really understand how you can use these quantum computers to model quantum systems. Now, the stuff that I've been working on with QuEra involves looking at quantum optimizations, looking at variational techniques, and continuous time quantum walks as a tool for algorithm design and analysis. It's also useful for benchmarking. So it's Edric that's been leading this, one of my team members. We've been working quite tightly with Jing and Jonathan, who are at QuEra, to look at essentially state preparation, optimization, and applying different sort of techniques to kind of explore how you can prepare states, but then also once you have a prepared state, you can then have it evolve as well. And I will mention before I go on that some of this work, I mean, all this work is leading to open science and research, right? So we're doing research outcomes, but it's actually quite strongly tied with the team at QuEra. So there we get research outcomes, but it's of interest to the broader community as well. So they're very interesting sort of projects that we're working on with QuEra that span a gambit of projects, and I'm only giving you a little taste of what we're trying to do. So on that note, I will move from the project and actually go to a notebook. And this notebook, we can pass along. It's a notebook designed to kind of walk people too. So depending on your expertise, you might find that the actual algorithms are not necessarily very intuitive, but it's also really an exploration of how you use the Rieber Hamiltonian to solve a problem, right? So this is an introduction to blockade analog. And then Atoshi will talk about blockade digital, and you'll see a lot more of blockade digital, but there's quite a bit of power in Aquila. And just on a side note, it's very interesting that, as Tomas mentioned, Aquila is up a lot, whereas some other computers are not up that often in terms of uptime. And if you're trying to do actual real experiments on quantum hardware, it's nice when they're up. It's been very good to be able to access a computer that is up quite a bit of the time to do some of this experimentation, to look at some of these algorithms. So on that note, I'm just going to walk people through some of the notebook. And I think, I mean, we'll hand this out. You can obviously download this from GitHub and then download the appropriate requirements, like pip install requirements, and then walk through and see if it is useful. We also have completely available, publicly available, a bunch of notebooks related to the actual research we're doing. So people can have a look and see what they might find of use to actually run, submit jobs to Aquila, receive jobs from Aquila, process jobs, post-process, and so on. So the Hamiltonian that governs Aquila, I've put down the general Hamiltonians with ground states, the Rydberg states. This isn't the complete Hamiltonian because we've tried to simplify it. So there is also not just a global detuning that Aquila allows, but you can do local detuning that are based on specific items. There is an interaction term, and then there's the Rydberg Rabi pulse. The interaction term drops off as R to the 6, and this is a van der Waals interaction term that can drastically change the energy, so you can get this blockaded space. I'm going to go here. So the Rydberg blockade, people can read the full notebook when they would like to, but I'm just kind of walking through some of the steps and also walking through some of the code. So the neutral atom technology generates entanglement via Rydberg blockade, and that's because two atoms simultaneously driven toward the Rydberg state upon shifting atoms energy through the interaction term. Yes?
Pascal, I apologize for the interruption. We have a participant asking how we can access the notebook, and we were wondering whether make it available to the...
Yes, it is GitHub.
Excellent. Thank you, Pascal.
And I will
interruption.
I will put this here, so on. So there we are, and it's a similar notebook we actually ran for a workshop in Korea. So but it's exactly the same. So you can git clone. We'll put this maybe into the chat so that everybody has it. Answered. There we are. So now it's there. And let me continue on. Right. So also I'll make a point that some of the material you'll have here, it'll work, but of course this is blockade analog. And so you might want to try to do some exploring of blockade digital, but they are both very informative. All right. So let me close this. Right. So you had this interaction term, right, that ensures that there's an energy shift to, ensure that the doubly excited state is off resonance. So you can't get the Rydberg states, which are mapped to 0 in sort of the results that you get from blockade analog. So you can't get a 0-0 state if there's a strong interaction term. You're unlikely to get a 0-0 state. And you can actually do the simple tests by running a little program. So this is blockade analog's import of chain. This basically generates pulses of the system and placement of atoms. And here there's an assignment. So you can see program assign. It sets the lattice spacing. I'm not going to go through the units because that's probably too much details, but I just want to get a flavor of it. So obviously if you place two atoms very close to each other, so the blockader radius, you'll basically not get the excited state, the doubly excited state, so 0-0. And you can see if I put run this, in this case it's simulation, it's not submitted to Aquila, but if you submit it to Aquila, you'll get basically the same results. Running 100 shots, and in this case, there's a even spread of all the essentially the states, roughly with 1, 1, 0, 1, and 1, 0, but no 0, 0. And we can actually just look at the histogram of going through and doing different lattice spacings. So two atoms placed together at different spacings, doing a simple Rabi pulse, and essentially evolving the system. And that evolution of the system, the two atoms close enough together, will suppress the 0, 0 state till they get far enough apart, and that interaction term ends up starts dropping off, and you can get some 0, 0 states, and eventually you start getting lots of 0, 0 states if they're far enough apart. This blockade radius is really critical for atom placements, but also the pulses that we can apply to the system, if you go back to this Hamiltonian, really allow a lot of interesting physics to be explored, but also very interesting algorithms to be explored. So let's go to maximum independent sets, MIS states, right? So this is a pretty standard problem, and Aquila is very well suited to this problem, right? Where you're trying to find the largest set in which no two vertices share an edge. So we again look at a distribution of some graph, and we want to make sure we can split up this graph, color-coded as it were, so that no vertexes in one particular graph share an edge. So here we've got reds that never share an edge with another red, and we've got now an MIS state. The fact that you've got a Rydberg blockade means quite naturally you can get this as a natural outcome of essentially evolving the system, of pulsing the system, going from a bunch of ground states to Rydberg states. And so by programming a suitable global Rabi and detuning pulses, one can steer the system from an initial state, that is basically all the ground states, toward a Rydberg configuration that corresponds to the maximum independent sets. And the idea is here that the key point here, I mean, it's NP-hard optimization, but the simple mapping of this physics means that Aquila can really tackle this quite easily, and MIS states can then tackle, if appropriately posed, a bunch of other problems. So Aquila lends itself to solving MIS-like problems based on the blockaded-based Hamiltonian. So as an example, we can walk through and solve the max 2-sat problem. So a max 2-sat problem is an optimization variant of classical satisfiability. Basically, you have Boolean clauses that are written in the conjunctive of normal form, and the idea is every clause is an or of two literals, and they can be negated or unnegated. And the idea is you want to find for the maximum number of clauses that can be evaluated to true. Now, this particular problem isn't necessarily meant to show that there's quantum advantage. It's more that you can see that you can pose this problem as an MIS problem and then have Aquila rapidly solve essentially the MIS of this. So why is it interesting, right? So it's a benchmark for classical approximation algorithms, canonically NP-hard problem that appears as a gadget in many reductions, and it's quite a natural starting point for quantum optimization because they map to the two-body problem. All right, so why is it jumping? Let's see. Okay. All right, so we want to construct a graph, specifically a conflict graph, and we can think of a conflict graph as the MSF graph by just basically posing vertices having flaws being true or false. So this is, we've got x equals 2 equals 0, x equals 1 equals, x2 equals 0, x2 equals 1. Basically, you have a couple of clauses. And of course, these x equals 0 and 2 are exclusive. They can't be both. So you have, you don't want to connect this edge, but you do want to connect clauses that could be related. So I have x2 equals 0 and x1 equals 1. I want to get an edge there. This is essentially the construction of the conflict graph, but it basically is an MIS, right? Because I want to have vertices, maximize the number of vertices that don't, that are sort of separated, so they don't share. That no vertex shares an edge. And so we want to convert this graph to a physical layout and essentially make use of Rydberg blockade to block edges that we don't want, right? So our goal is therefore to have atoms representing non-adjacent vertices must be farther apart than the blockade radius, so they can be excited together. And atoms representing adjacent vertices must be within the blockade radius to enforce this blockade constraint. So you can only get 0, 1. One of the ways that we've done this, but there are multiple ways of doing this, is to actually construct the position of atoms. And one of the ways to do this is actually network X, which is a nice spring layout for distributing vertices, where you can make use of network springs layout to randomly distribute a bunch of nodes and then spread them out so that you get long, distances greater than some value and shorter than some value. So this is quite a good way of doing it. We've got a minimum radius. I will say you'll notice in this notebook that there might be values that seem arbitrary. So you're like Y6 and Y6.5. Blockade has very specific units in which it operates in. So blockade analog operates in this case, micrometers. You can see here in this plot. And there is a minimum distance in the actual hardware, which ends up being about 4. But also just for simulatability, it's easier to have the interaction terms be not a dominating interaction term. And so you can just do a simple blockaded space and not have to fully calculate the interactions. And we use this as 6, where the blockaded radius is 6.5. So if they're inside the blockaded radius, they'll be blockaded, right? They won't be doubly excited, but then outside they'll be fine. And they can be as far apart outside as they want. This then method distributes the atoms that would actually be positioned on Aquila. So Aquila would distribute these neutral atoms as best as it can, considering there's a grid. And then Aquila would then, would actually start pulsing the system with lasers and then do a measurement at the end. In this case, we're going to do something similar, but obviously we're not, there's no grid here. These are just exact values for atom positions. There's no noise in the system. So we've got an atom arrangement that ensures that atoms that are meant to be representative of a specific vertex, where we don't want them to be excited at the same time, right? Specifically, atoms that are adjacent must be within the blockade radius. So we've got 2 atoms that are adjacent and they're within the blockade radius. There's another 2 adjacent atoms that are in the blockade radius, but they're ones that are further apart. They're not in the blockade radius, so they're kind of independent, or at least they can be doubly excited. Then we want to define a cost function to find a near optimal solution to the problems that minimizes the average measured MIS costs. There's a bit of boilerplate code here to do calculations of expectation values. The big thing now and for Aquila is actually designing the protocol. And there's actually 2 ways of doing this on Aquila. So it's an analog computer. You can adiabatically evolve the system, right? So we have some Hamiltonian. You can adiabatically evolve the system so that it slowly tracks and you stay in the ground state of that Hamiltonian, and then you'll get to the ground state, the Hamiltonian's ground state of being the MIS state. You can implement this with linear ramps of the global Rabi drive and the global detuning. You just have to have them be a slow enough change so that it stays as an adiabatic evolution. And the nominal statement here is, let's start off with the maximum. So you have the Rabi drive at the maximum of the hardware value. So this is the maximum that actually Aquila can achieve in terms of the Rabi drive. And you basically are going to ramp this down slowly. And the global detuning starts off basically at 0 and then slowly ramps up to maximize the negative impact of the Hamiltonian. So if you look back at the Hamiltonian, at some other time, t, you have an interaction term, and the global, this Rabi drive is gone, so it doesn't contribute, but you've got a global pulse that will be a negative contribution. And so you'll kind of really be dominated by the configuration with the most excitations, which is the maximum independent set. And so you can do this a simple adiabatic evolution. Again, you'll notice here, we're starting off at t equals 0, t equals some time, and the global detuning is at hardware-based maximum. So you're just basically driving the negative as much as you can. If you look at the pulses that are going to be doing this, so we're looking at the pulses that are actually going to drive the system's evolution. We're basically ramping up the global detuning and ramping down the Rabi drive. And the interaction terms are staying there, right? So there's still some interaction terms. Once you have a program, you can then evolve the system. And in this case, we're looking at prog is coming from blockade analog. You specify the pulsing of the system, and then you can evolve the system. What we want to do here is obviously figure out what is an optimal time to evolve it for. So let me go back here. So this is the adiabatic evolution, and there's some optimal time that we want to evolve the system for. And the optimal time for this particular setup ends up being about 3.5 seconds. And there's a maximum time that you actually want to run the system for because of essentially the decoherence of the system. So we're looking at the adiabatic evolution kind of running for 3.5 seconds. If we then look at what the actual output is, so this is basically trying to figure out what the a simulation for, I mean, I can get the results out of this, but like what is the best time to maximize the likelihood that you pick up the optimal solutions, the maximum independent sets. And then we can run for a large number of shots. I'm not going to go into the too much details, but the idea is that we've got a nice little parser. You can see what is the best set. And so we're looking at a large set of atoms. So if we look at the back, if I go back up to the atom count that we're doing, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms. And the result is that and these actually end up being the correct solutions. The dominant solution is there are two, where you can get the best solution is here, mostly satisfied with one unsatisfied, and the next best solution has actually got two unsatisfied clauses. So it is the next worst lot, and you can see in terms of number of counts, I've got 62 being the dominant count. So the most often found solution is the dominant correct solution for this particular problem. The next most found one is not terrible, but is to be expected. So that's one approach. But one approach that another approach that's actually been something that we're looking at research is actually coming from looking at Grover's search. So you're looking at an adopted ansatz for alternating unitary structure of Grover's search, or an approximate optimization algorithm. And specifically, this is a quantum walked-based ansatz. And this is a very different approach. We're not necessarily looking at adiabatic evolution, which will definitely guarantee that you get pretty good results. We're trying to see if we actually shorten the time and get better results out of different approaches. So this is the algorithm research we might be doing. And in this case, this ansatz is to prepare a pi/2 pulse. So you get a uniform superposition inside the blockaded subspace. So all blockaded subspace, you got zeros and ones. And then you start trying to do a phase marking to separate out some states. In this case, the real approach would be to optimize that pulse for the global pulse, or even using a Rabi, another short Rabi pulse to get some separation between the various states. We're just using a pi/n. And what we're going to try to do is actually infer what is the best walk time for the second Rabi pulse that we're going to apply. So I'm going to do a Rabi pulse to get superposition, a phase marking, looking at the global detuning, and then we want to do another pulse to essentially drive the system to amplify the states we want. In this case, there's a second Rabi pulse that we're going to apply. It's dependent on this Rabi pulse. Here's the warp time. We actually also try to do a minimum. So it's, again, this is just kind of hardware and simplification for simulation, that there's some minimum floor that we want to walk for. And then we're going to do this type of pulsing that we're going to do in the system. So I'm going to show it here, where there is a pi/2 pulse, another pi/n pulse for the global detuning, and then a final pulse. And this pulse time is what we want to optimize. We don't know what it is yet, but we can figure it out. We can look at optimal values by looking again at the cost. And you can see eventually sort of a walk, and you get down to a certain amount of time being the optimal. And in this case, it ends up being 2.7 microseconds for the system. So this is a very different approach to doing this algorithm. We're not just trying to like slowly walk to the ground state. You're trying to drive evolution. And so there is a pulse that would kind of give you the best separation out of the various states and give you what you hope is the MIS state. So once that's done, you can play with the different number of atoms, but you'll see again that we get a statement where the only one clause is unsatisfied as the best, most optimal, like amplified state. There are obviously a bunch of other states, but they're just part of the space, right? So it's not like it's amplifying four states. They just, not completely unpopulated. And the next best state is also a one in which only one clause is not satisfied, which is slightly different from what the adiabatic walk produced as the second best state. So the two best states produced by this walk actually end up solving the problem a little bit better than the adiabatic approach. And the idea here in this notebook is it walks you through how to set out amplitudes for Aquila or amplitudes for blockade analog, run evolution of the system, and essentially get a solution for a MIS. But in this case, it's specific for the problem of the max 2-sat problem. And so you can start having, hopefully this notebook is informative for you to start exploring how you might want to pose problems for Aquila that would be maybe MIS-like. And then there is a specific element which is not adiabatic evolution that's informative for you. You could try something. The main reason you want to maybe explore this is that adiabatic evolution, you are limited to 4 microseconds. So if you can shrink the amount of time that is needed to run the system to within 4 microseconds, because maybe the optimal time is outside 4 microseconds if you did a simulation of it, you actually can't run that not sort of optimal adiabatic evolution. Whereas the walk might be able to pick out a shorter time scale so that you get a better evolution in a short amount of time. And that is the notebook. I'm happy to follow up on questions and maybe walk through a little bit more. But I think it's a useful basis to kind of also start thinking about blockade digital, because essentially the pulses that are being applied here are somewhat kind of hidden behind some of the stuff that's happening on blockade digital, because you're trying to drive essentially atom evolution. And this is more on the analog approach, but also gives you a view of the pulse control that might be happening. And I will stop there. And actually, I will mention one last thing before I hand over to Tommaso. And I'm going to share again. Sorry, Tommaso, I totally forgot to mention that. So we are very keen to collaborate, as I mentioned before. And in fact, looking to do this for the next round as well. There are Australian funds specifically to collaborate with Indian research partners. So if you, wait, I'm not sharing, am I? Let me share the pic, desktop, share. So there's an Australian Indian Strategic Research Fund that's available. And one of the main focuses of this fund is AI and quantum computing. And so this round is closed, but there'll be other rounds. And there's an equivalent fund in India as well that mirrors this fund. And so if there are quantum computing projects that you think QuEra, Pawsey, and the Indian collaborators can work on, have a real think about it. Because there are funds available to actually fund postdocs, researchers, purchasing of infrastructure on the Australian side, and there's something going on the Indian side. And there may be some really, really fruitful collaborations that can come out of this. And with that, I'll hand over to Tommaso.
Excellent. Thank you, Pascal. It was really a beautiful presentation and highlighting the qualities of QuEra's devices and the opportunities for collaboration with the Indian ecosystem through Pawsey and QuEra. With this, I would like to give the stage to my colleague Anshuman, who will talk about the advancement in photonics within QuEra. Anshuman, the floor is yours.
Yeah, thank you, Tommaso, and good morning, everyone. Happy to share some of the big progress of photonic integrated progress, here at QuEra. So as we've been saying that to make one of the primary goals of the quantum computing is to make a fault-tolerant quantum computer, and there's a scalability issue. So in the next few slides, I would like to give you a brief overview the scalability issue in the context of the neutral atom quantum computers and how we're trying to solve it using a photonic integrated circuit here at QuEra. Yeah. So when you think about the quantum computing with neutral atoms, so there are three building blocks we could think about. So atoms, of course, as a qubits, and then you need some kind of assembly to arrange those atoms and then do the laser gate for those logic operations. So all of these things happen optically. So one of the simplest cartoons shown below in this picture is the what's happening in the machine, and it's all optics. So it's like a wirelessly controlling the qubits, and which is very powerful, using a neutral atom as your qubit. Then because as a optical mode, you because optics allows you to have access to the millions of optical mode in a field of view of an objective. And these atomic qubits are trapped, of course, using a movable laser tweezers, and then we use laser to do the gate. So depending on the type of lasers and the laser configuration, you could do single qubit gates or multiple qubit gates. So it's not a smooth sailing. There are some outstanding challenges doing the controls, photonic controls for the atomic qubit. And if you have seen in the recent years, number of qubit grows very rapidly. But however, if you think about the number of controls of these qubits has not grown in the same pace. And currently in the machine, there's a lot of serialization and multiplexing is done to actually control these atomic qubits. So having an independent control of these atomic qubits is very advantageous if you could think about it. So for a fixed number of operation, it would increase the clock speed, and directly you can also increase the number of operations if you have a more independent control. So it's like a little bit more complex design space. If you think about, as I said, you probably need a million qubits for a fault-tolerant quantum computer, and even at the scale of the logical qubit level, for example, 100 qubits, having an independent control for those 100 logical qubits is not very trivial. So it's a very complex design space problem. So and other restrictions come from the time scales. For example, if you want to do a read work state, it could be 10 nanosecond time scale we're talking about, and for the beam trapping, it could be up to 10 microsecond. And for those who know photonic integration or PIC knows that most of the development of PIC happened at the telecom wavelength, which goes from 1300 to 1600 nanometer. So this already restrict what kind of technology you could use. For example, in the atomic space, the wavelength range you would like to access is between 400 to 1100 nanometer. So again, it limits the type of material we could use. So when we design our PIC, we have to think about all of these variables. So here at QuEra, we are developing a photonic integrated solution for atomic qubit control. So first of all, this PIC is a wafer scale. That means we can fabricate hundreds of devices and many chips on a wafer, and it manufactured in a chip foundry, so it's like a very highly scalable. In terms of speed, we could get up to a nanosecond speed depending on the technology we use. And once you make this design for this photonics chip, your output pattern is more or less fixed. But that is fine, because it could if your application is already fixed, so that's not a big problem. And one thing also take into account that this developing this PIC platform is like a long development cycle. That means you have a design, then the fabrication, and it happens multiple times. So this one thing you have to take into account. So once this development cycle is done, we get a one functional PIC chip like the one I show here in the bottom. And how this works, that you have a laser input goes to this chip, and this chip, like photonic chips, divides this input into multiple channels. For example, 8 channels here, and these 8 channels goes to the 8 modulators, which basically is a high contrast switch. And by controlling the voltages to these modulator, you can like generate like a optical output pulses with a desired timings. So as is shown here on the right side. So next problem comes how you can interface with this with the atomic microscope. So that's another thing we have to think about while designing this chip. So this is more or less the overview I have for the PIC at this time. And we are soon going to submit something to archive, so keep an eye on it. And with that, I would like to pass the torch to Ashutosh, who would going to speak about the application side of the quantum computer. Over to you, Ashutosh.
Thank you, Ashuman. Ashutosh, the floor is yours.
Yeah, can you hear me?
Yes. Can
you see the slides?
Yeah.
Okay. Yeah. So I guess like I'm in India. So good afternoon, everyone. Most of the audience, I believe, are from India as well. Yeah. So I'm from the application side of things. And in this presentation, I'm going to be talking about the path to quantum utility, how we see that path. And, we believe that analog, digital, and logical neutral atom quantum computers are going to be present to achieve this path. So beginning with like introduction of the next few slides that I have, I'm going to be talking about the past, which was like, predominantly we focused on the analog mode neutral atoms, and Aquila was our product, like, and still is the product, And after that, I'll be talking about the present focus, which is on realizing digital or gate mode of quantum computing. And we're developing the Gemini class of quantum computers, as you have already seen in the previous few slides. And I'm gonna be also talking about the future, which will involve like logical, qubit mode, which through error correction will enable us to implement fault-tolerant quantum algorithms and really, get to quantum utility. So starting from the basics again, like, sorry if you have already seen these, but, the core of the neutral atom quantum computers are, arrays of individual rubidium-87 atoms. So the qubits are associated with the energy levels of the rubidium-87 atoms, and, you can manipulate them using highly coherent lasers. So, talking about Aquila, like Aquila is QuEra's cloud accessible computer. It has been available since November 2022 on the AWS bracket. So the idea is that it implements time-dependent Hamiltonian dynamics. So the Hamiltonian, time-dependent Hamiltonian, here you see, you have seen this expression before, but just to repeat, this is the field, driving fields frequency as a function of time. You have it drives the states from ground to side state, which is a Rydberg state. Then you have the tuning parameter, which can also be seen as an energy penalty. And then finally you have the interaction term, which basically injects the correlation into the state. So ultimately we are doing Hamiltonian dynamics. So yeah, we are implementing something of this here. But since we're analog mode, we don't have explicit 1 and 2 body gates. We do the time evolution explicitly. The gates we can think of as those gates. We can think of it as many body or all-to-all gates. And you program your problem into like positions of the atoms. For example, this is a snapshot of a given arrangement of atoms, and you want to encode your problem in such different geometries of atoms here. So since many of you have got this 1 hour access, I included this job script that you want to submit to Aquila. So this is a sample script, self-contained script here. You import the dependencies here, which is like the blockchain open source dependencies here. You can find with GitHub and install them. You have to define some environment variables for the backend. You will get your magic key, I believe, through the email, and you populate these environment variables. You define some program that you want to run, and then you just have this call this interface function to run the job, and then you basically use it through the exclusive access flag here. And I believe like you can use similar interface to if you run through AWS bracket as well. You just replace this QuEra kind of flag with bracket or something similar. So Aquila, as you know, has already been there for more than 2 years. So a lot of exciting science has already been done using Aquila. And as mentioned before as well, we mostly worked on 3 trust directions, which is like the optimization, like starting with optimization, which is again, as we saw earlier, that you have to, you attempt to solve like hard combinatorial problems, on the quantum computer here, and using like native features of the hardware. Then you also have the simulation, as Feynman said, the best way to simulate quantum properties in nature is through quantum computers themselves. So this is the simulation part. And then of course we also focused on the machine learning aspects where, this is just an example work where, the quantum computer is basically being used as a kernel or a reservoir, to generate high quality feature data, and then, they can be trained on a classical kind of computer, using classic regression models. And I'll talk about the results that we got on this project and the other works as well. So, as you already seen before, like this is the maximum independent set optimization problem, which is can be easily mapped to the QuEra hardware. And this is one of the early, first landmark results by Harvard or QuEra in 2022, where they attempted to solve the MIS problem on unit disk graph. So just to repeat again, the MIS problem is for a given graph, you have to find like the largest set of nodes, such that your node to nodes in that set share an edge or are not adjacent. So this is generally an NP-hard problem. So this was done in this work here I mentioned. And so in this work, they showed that they got like hints of quadratic speed up, by employing these MIS mapping on Aquila. Another way, so to be able to capture other combinatorial problems, that occur in different areas, you have to go beyond the unit disk independent set, and there are different ways that you can attempt to go beyond it. Like one is the non-native hybrid algorithm technique, where you basically embed the optimization problem in a larger quantum classical workflow. And then your quantum computer is both basically can be seen as a coprocessor. So instead of just finding ground states, it can basically provide hints to the classical solver. Those hints can be in form of distributions or densities, not just the solutions. So this is one such way. Another way is through using unit disk MIS encodings, where you encode the arbitrary combinatorial problems and make use of reduction to transform the problem into a maximum weight independent set problem. So here you put weights in the vertices of the graph, and then if you want to solve something like a QUBO problem, all you have to do is modify the weights of these vertices to be able to get a minimum for the cost function. Another way to do this is to use machine learning, combine it with machine learning. So use the quantum device, for example, as a sampling kernel for something like a variation autoencoder. So this way we can efficiently sample the Boltzmann distributions and send it to the classical kind of solver or the autoencoder. So we worked, and this is like moving on to the simulation part. There has been a lot of works done in this regard. And the idea is that, these systems, all these quantum phenomena like confinement and string breaking, frustrated magnetism, the quantum spin liquids and others, the many-body Hamiltonian occurring in these quantum phenomena are very similar to the Rydberg-style interactions that happen in neutral, in our hardware, So these are like very easily mappable to our hardware. And, these works basically made use of Aquila to simulate these phenomena quite efficiently. And, mostly like, you start with a lattice of atoms, and then, you want to prepare like, these non-trivial ground states occurring in these kind of phenomena. And you mostly use like adiabatic, adiabatic evolution to start with something very simple state, all zeros probably. You do the adiabatic evolution to arrive at, ground state for this. And then you do like further processing, like quenching and other things to extract and probe from that ground state. Finally, like we looked at the optimization angle, we looked at the simulation angle, and now, we're looking at the quantum machine learning experiments that were done on Aquila. So here, as I said before as well, like here, quantum computer is basically being used as a quantum reservoir or a kernel that generates like feature vectors, for a given data. For example, here you do the classical pre-processing for this image of a horse or for time series prediction, and then you embed it or encode it in Hamiltonian dynamics. So how do you do that? You make use of the global pulses. You make use of like a time-dependent, tuning, detuning. You kind of shift the positions of the atoms depending on the image at play, and then you can also do like a local tuning as well using like local pulses. So then you do like time dynamics. Once you encode the problem here, which is non-trivial, but and hard to do classically, and then you generate this features vector for a different like image, for a given image, let's say, and then use regression to kind of do your prediction. So this is like a pretty promising approach in the sense that you don't do any training on the quantum device itself. There are no gradients involved here. The training actually happens here, but the feature vector that you get is highly correlated because of the fact that you can do the quantum dynamics, on a much larger, dimension. So this is highly accurate, and there are a lot of advantages over variational QML. For example, this is like renewable, it's resource frugal, it's more noise resilient, it's working in the analog mode, and is highly scalable as well, as you will see in the next slide. And of course, this one will be classically intractable to generate such a feature vector. This was like one of the largest scale, QML experiment done so far. Actually, I would say the largest successful, QML experiment, because Google also did like something like with 40 qubits, but here, they made use of 108 qubits to do this kind of experiment. Here, they mostly use like this disease, this leaf iterator data from that repo, basically, and they use it to classify whether the leaves are healthy or diseased. And here is like this plot here shows some results. You can see as the number of qubits increases or the number of size of the feature vector increases, you can see the orange curve is kind of picking up the accuracy, and while the comparable classical models kind of saturates. So that was quite, I would say, encouraging. And yeah, so that was like the analog mode kind of work that had been done and still being done by multiple researchers all over the world, actually. And switching now to the digital mode qubits, the same slides, the same slide as before. And what changes is, you had the analog mode here, which was like between the ground state and the Rydberg state. The Rydberg state is highly sensitive to environment because of the diffusivity of the electron cloud in that state. So here we were coherently driving the dynamics with the Rydberg state using this 2-photon transition before. And now in the digital mode, what you can do is you can encode the qubits to a hyperfine state. So here, like 0 and 1 basically define the the qubits, the digital in the digital mode. So you can use like for using like for implementing single qubit gates, you can coherently drive dynamics with hyperfine states using Raman transition, and then these hyperfine states, since they are in the ground state manifold, they're insensitive to the environment, and they're not excited. They're in the ground state manifold, so the coherence time is increased. It's in the order of seconds, or even minutes, which is quite good. So, and one of the most attractive features in the neutral atom quantum computing is the Rydberg blockade. And you can have like robust entangling gates enabled by the Rydberg blockade. So what it is like, once you have the Rydberg excitation, only one atom can go in the Rydberg state. So all the, remain like all the adjacent atoms, they cannot be excited to the Rydberg state because of this phenomena. So you can remove multi-Rydberg states, exclude them from the dynamics. So this is like one little cartoon here, which shows like, pairs of atoms here with different spacings. Like within the pair, you have 2 micrometer, and then, between the pair, you have 10 micrometers. So when you shine a laser, you will get like, in parallel, all the entangling gates here. And, it can basically, there was an experiment done by the Harvard group where they looked at the, the fidelities of the control Z gate in this operation, and they were able to achieve 99.5% fidelity, which is quite, accurate and pretty encouraging. Naturally, you can extend the Rydberg blockade to multi-qubit gate. So you put 3 atoms together, and you get like a 3-qubit gate quite easily. And if there was an experiment where they looked at they increased the number of atoms, and they were able to achieve like 98% fidelity for the CCZ gate, which is like basically equivalent to a Toffoli gate, removing the hydromerts. So, in some sense, like since decomposition of a Toffoli into a CZ is also quite, expensive, and then all the atom moves which are involved in this decomposition is also expensive. So it might be worthwhile to directly work with a CCZ gate, using these 3-qubit or 3-atom arrangements in the future. So to basically, use our digital modes, a quantum computer, we need like a native gate set. And the most obvious gate is the control Z gate that can be realized. But, as you have seen, like we can technically extend this control Z to CCZ, CCCZ, or, multi-qubit gates if we have the right fidelities, in the future. But for now, we are mostly concentrating on, control Z for now, but in principle, it can be extended to multi-qubit controls. We also have like control Z phase gates, actually, and, like these gates basically can also be, generalized to this permutation symmetric Z phase gates. Of course, like to be able to do like universal fault tolerant quantum computation, you need the arbitrary 1-qubit rotations as well, which can be done on a hardware. This is like a very neat thing associated with our gate-based quantum computer, Gemini. So here, we have like a zoned architecture. So our whole quantum computer is basically divided into different zones. So here we have the storage zone where the atoms are stored here, bound by the optical tweezers. This is a reservoir. In case of atom loss, you can replenish the storage zone from here. Then this is the entangling zone. So you kind of bring the atoms from the storage zone to the entangling zone, tear the laser, and and create the gates. And then if you want to measure them, you can just carry the atoms further to the readout zone, do the imaging using camera, and basically use it to do the feed forward operations. So this zoned architecture makes things very scalable. for us, the controls are much easier, and then the number of moves can be like made. There can be a lot of parallelism in the way we do quantum computation or circuit execution. So this is like example of a Gemini class of machine currently in ICE, Japan. And to be able to see like what I mentioned in the previous slide, this animation is basically showing these atom movements. You can see like, yeah, the atoms are being moved from the storage zone to the entangling zone. And then once they are close together, just the laser flash is the entangling gate. So basically users can specify the SLM sites, and then you have the dynamic AOD to move the atoms from the storage to the entangling, then bring them back to the storage one. And this basically, this ensures very high fidelity local and global gates. So this is a slide where we, look at the highlights of this neutral atom quantum technology. So we have high fidelities enabled by the high fidelity rubidium natural atom qubits. These, as we saw, 99.5 and 5% fidelity for the control Z gate. This architecture is massively scalable. You have the optical controls. Because of the optical controls, you have the AOD in a 2D moving atoms around. We have technically this is scalable to many qubits, but the signal requirements is not as drastic. You can control a number of qubits with the same signal to the global pulses. So this is like scalable to thousands of qubits in principle, or more in principle. And then of course we have we don't have a connectivity per se because we can move things around. So we don't have a native connectivity that you see with superconducting modalities and other modalities. We can move atom around, so we can achieve any kind of arbitrary geometry in principle. And of course, we can get a lot of 2-qubit control Z gates. For example, this is a cartoon of a circuit. We can do all of these things in parallel, on a hardware. So all these things basically make this modality quite exciting to basically extract quantum utility. Pretty soon, the Gemini enables a world of gate-based list applications. Here I have mentioned some that we have been involved in at some point or are currently working on. For example, for the simulation, you already might be aware of the variational quantum eigensolver, the QP, the quantum phase estimation requiring the plotter, the 1 kilo ground state states, and also it can be basically extended to the financial domain with options pricing. Of course, we saw in machine learning, you can do digital reservoirs, quantum neural networks, classification. So all these basically applications that are there that can be done on other modalities like superconducting can be done on our hardware as well, basically. Now, we covered the analog one, the digital mode, and now is the logical mode. So let's say this is a logical qubit. Now we know that generally a qubit is mapped to a 0 or 1 state or the energy levels. But a logical qubit technically is not just coupled to an energy level of a single qubit, but you can see it's mapped to multiple atoms or multiple qubits. And the reason is because that allows you to do quantum error correction. This is similar in spirit to graphical error correction, where you add redundancies to the information and do a majority voting to be able to decode bit flip errors. So in similar way, you kind of encode a logical qubit into a code block of atoms or qubits in our case, atoms in our case. And, the only problem is things are much more complicated now because of the no cloning theorem. You cannot just copy information and because of the XZ measurement issues. So this is let's say you want to do entanglement between between two, let's say, logical qubit. A logical qubit will be an array of atoms, as you saw here. This animation shows you entangling operations between two logical qubits. here. So what you do is you bring the qubits, again, the two logical qubits, into the entangling zone, and then do these entanglement operations. One way to do this is through use of transversal gates. So these transversal gates, you basically, for an entangling operation between two logical qubits, you apply corresponding entanglement between the atoms in the two layers, or the two code blocks. So in some way it is already fault tolerant because there is no error propagation in the transversal kind of gate technology that we employ on our hardware, because it's very easy. You can do a lot of things in parallel on our hardware. So we make use of transversal gates to do entanglement operations between logical qubits. So we already know for true quantum utility, efficient error correction is crucial, and QuEra is one of the leaders, I would say, in developing in developing like quantum error correction and based logical qubits. And of course, like, the core design principle is very important. The choice of error correcting code as well as the circuit construction, they have to be tailored on on the specific system you want to solve. So a code design is going to be very important if you want to extract maximal quantum utility. So here, like, for doing like universal quantum computation, we need a universal gate set. But according to the Eisenstein-Mills-Norgaard theorem, we cannot have a universal transversal gate state. So transversal gates are not going to be enough if you want to have universal quantum computation. So what is the approach to achieve universality? Well, you can use transversal gates for most operations, but then we can make use of this magic resource state to help implement the rest. And one way to do this is basically the T-state teleportation technology, where you prepare the resource code and teleport it to the circuit whenever it's needed, because basically that we need like Clifford plus T gate set for universal fault tolerant quantum computation. So you can prepare those magic states, and to ensure that they are high quality, you can carry out magic state distillation to increase the fidelity of the T states and then teleport them as needed. So in December 2024, QuEra was, I think, one of the first in the community to do experimental demonstration of MSB using this Gemini class of machines. We can refer to this paper here. So this was the machine where this MSD experiment was done on. So the idea is that you basically have some low fidelity magic states here, as described by a smoosh of the cloudy smoosh here on the block surface. So these are the lower fidelity magic states, and then you basically do distillation using a few copies of them to achieve a high fidelity T state, as basically described by a smaller spread of the color here, and then use it in your computation. So in principle, if you use more and more copies or more like rounds of distillation, you can get like really high fidelity magic states. So in our work, like, we mostly use color coded quantum error correction code, like with d equals 3 and d equals 5 distance codes, and then basically we tailored the code based on our hardware strength. So for example, these are if you assume that these are the 5 logical qubits, we can do these operations that are required in the magic state distillation by again moving blocks together, entangling them as needed. So yeah, so the reconfigurable hardware is kind of helps in getting the distillation done very efficiently. We have the control parallelism, and then talk about the decoding aspects. Next slides. So we found up to an 8 times gain in the magic state fidelity from the distillation, using distance 3 code, and we got like a 5 times gain using a distance 5 code. So here you can see, like, in this graph, this is the input, the injected fidelity of the magic state, and at if you go on the left of the graph where you have less fraction of the measurements that you take, you discard most away, then you get like a very high fidelity of the magic states, and you can see. So there is a trade-off, if you basically if you're accepting more and more measurements, then the fidelity drops. But if you accept less and less fractions, then your cost goes up, but your fidelity also increases. So you have to find that balance, I guess. And finally, like the slide basically talks about like the advantage of transversal gate, how it ensures algorithmic fault tolerance. So the idea here is that the transversal gates allows reduction of the syndrome extraction rounds in the error correction. So instead of OD syndrome extraction rounds, you get like a O1 round, which can lead to 10 to 100 times logical clock speed up in the fault tolerant cursor. The idea and the core concept here is the correlative decoding. So instead of like basically looking at the blocks of different circuits and doing encoding, you have to look at the full circuit and do the encoding. But the problem there is that the decoding becomes more complicated because you have to look at large circuits, so it becomes computational expensive on the classical sides. So you might have to leverage GPUs to do this real-time decoding. But then on the hardware side, you save a lot of clock cycles, in the error correction. So once we have the let's say full error correction, we basically have the real quantum utility, which can be used to do a lot of different tasks, as we already saw before. So, and this basically is slide where is basically captures like what we can do when we have, let's say, these number of logical qubits. If we have like tens of qubits, we can do some demonstrations, like NSB demonstrations really good. If we have like millions of kind of logical qubits, we already know like it can be used for like break-in encryption, other areas as well. If we have thousands of qubits, we get into the early utility phase. We can do like a lot of quantum chemistry based simulations here. But what is also quite exciting is what can we do with the hundreds of logical qubits, which we are expected to achieve in the next few, like 3 to 4 years maybe. So that's a very kind of exciting research direction. It seems like we will have to make use of classical and quantum computers together to be able to hit quantum utility for both regime of logical qubits. But this is something which we are kind of actively exploring. Finally, like just a slide where we basically are involved in this Welcome Leap project, which the aim of this project was in 3 phases, and we had like results of in each phase where teams were basically excluded based on the performance. So happy to let you know that QuEra is in 2 of the 6 final teams for the phase 3 program of the Welcome Leap. And the idea here is that we have to demonstrate that our hardware basically solves a problem of quantum of biological significance that are hard to do on the classical quantum on the classical quantum chemistry based model. So we are looking at like ligand protein binding affinities, NMR quantum simulations, and other kind of projects within this Welcome Leap. So with that, I kind of have finished my slide deck, and I'm gonna refer it back to Tommaso.
Thank you so much, Ashutosh, for the great presentation. I would like to thank all the hosts, my co-hosts today, Pascal from Pawsey, Anshuman, and Ashutosh from QuEra. And of course, I would like also to thank everyone in the audience that stayed so far until the end of the presentation. I see really a large number of participants that made it to the end. I would like to reiterate that of course we will be happy to answer your questions offline, also after the presentation. Feel free to reach out directly to us, or if you have any specific question regarding the section that Pascal from Pawsey presented, feel free to reach out to him as well. I think the discussion that we had over the Q&A has been extremely engaging. I've seen several questions related to the implementation of complex algorithms with our analog devices. Some questions towards the end on the digital. There was an interesting question, Ashutosh, on the magic state side of the presentation, where you mentioned our most recent result on the distillation. I think it's worth pointing to our publication that recently appeared on Nature. Sort of for all of you that might be interested, feel free to read and eventually to reach out to us if you see any interesting way to collaborate or to connect with us in any way. So with this, I would like to thank all the participants for the attendance and my co-host. Thank you so much, and we look forward to hearing from you soon. Thank you.
Thank you.
Thank you.